Alright, so for this one, we're going to be going Centroid and Incenter. Um, they're pretty straightforward. And these are points of concurrencies, right, with Centroid and whatever the Incenter is. The centroids have to do with medians, whereas the incenters have to do with angle bisectors. So there's some special properties just with these two that we're going to look at. All right, first things first though is, right, we have to label all this kind of stuff. Remember, a median goes from a vertex all the way to the midpoint of the opposite side. So in this case, right, we just have to label our medians. And again, the median will start something like from and go all the way down to this opposite side, F. Right, so like a median would be B, F. Because again, as you can see, it splits the opposite side AC into half to congruent, so that's the mid segment, right? That's the midpoint. Other ones we got are like C to D, because again, makes those congruent. And lastly, the last median we have is A to E. Because again, the medians just go from a vertex to the opposite side. Whereas the centroid, right? The centroid is the point of concurrency for all the medians. So really what this means is that it's this point where they all meet up. So in this case, right, it's point P. Centroid is point P. And again, to tell whether or not it's a centroid or median, right, when you're going to see where it starts and how it's ending, right? So if it starts at a vertex and it hits that, that's the medians, it's all good. All right, the actual theorem behind it though, right, so the main idea, so the main focus about it is the centroid is 2/3 the distance from each vertex to the midpoint of the opposite side. Okay. But what this means, right? So for all of these, right, from B, the centroid, right? So this part right here, the distance from B to P is 2/3, right? 2/3. It's hard to see that. Whereas the distance, if this is 2/3, right, the last remaining half, again, out of 3 out of 3, how much you have left is 1/3. All right, so it's kind of a cool little thing that we kind of look at. Let me use a pen to kind of, make that a little bit darker to see, as opposed to what's highlighted. So it's 2/3 as opposed to 1/3. All right, that's a small little detail about that. Okay, and so kind of going through this, what this means is that, right, if you kind of see it in way, you can, if you have the full number, you can break it down to 3 different pieces and kind of try to find out what's going on. And so, like in this case, from here to here, right, the 2/3 part is that distance, like B to P, right? This would be like B, this would be P, and so our last part would be F. Where here we have our any vertex, we have our centroid, and then we have the midpoint. Right. Okay. So when we get to the actual like parts and stuff or whatever, when we actually get to like the actual examples and stuff, it'll make a little bit more sense when we can actually put numbers to it. But yeah, that's the idea, right? If you have the full distance from the vertex centroid, any single one of them, any one you look at, right? It could be B to P, it could be A to P, right? And all the way to E. It could be like this is C, this is still P, and then this is D over there, right? It doesn't matter, right? This is still 2/3 of the way, not half the way, 2/3 of the way, and this is the rest of the part. So the way you can kind of think about this, right, from part to part, if you have if you have the vertex of the centroid, and you're trying to get the other piece, again, this will make sense in a bit. If you have the 2/3 part and you're wanting to get the 1/3 part, that means you're going to have to divide by 2, or if you have the 1/3 piece in each piece, you're going to have to multiply times 2. and the parts of the whole. So this one kind of helps out too. If you have the 1/3 piece, let me switch these up. And you're trying to get to the whole part, which is a 3/3. Then in this case, you multiply times 3. Whereas if you have the 3/3, the whole part, and you're trying to get to a piece, divide by 3. And again, this will make way more sense when we actually kind of look through the notes and kind of do the examples or whatever, right? But that's kind of the idea. Right? Any centroid, the distance from here to here is 2/3 of the way, where this is just 1/3. All right, and the whole thing is the whole 3/3, the whole thirds. All right. Looking at the incenter real quick though. The incenter, the incenter theorem itself. The incenter, this one's pretty straightforward, is equidistant from each side of the triangle. So again, we have this word equidistant. So really what this means is that um, if this is our incenter, all right, so let's actually label this stuff. Our incenter, in this case, is point G. And the angle bisectors, right, are from A, right, angle bisector means these are congruent, A to F. Here on this side, it's C to E. And then here we have B to D. And so what this means is we have these congruent segments, right, from the all the way to the other side, right? So this little piece right here is congruent to this little piece right there, which is congruent to this little piece right there. Right? So all the congruent segments in this case are like kind of that midpoint, right? From this point from the incenter on. Not this whole thing, just this little piece. So like this would be like GE is congruent to GF, which is congruent to GD. And because all this stuff is congruent, since all this is congruent, right, it makes this really easy because this is all just equal to each other, right? So when we get to the examples, I mean, they're just a set equal to them. It's easy to find them, figure out what they are. All right. But yeah, that's it. That's centroid and incenter. Where is this?